Dear student, today I'm going to start about the next lecture, that is transmission laws of the optical fiber. For design of optical communication system, this transmission fiber play important role because the maximum transmission distance between the transmitter and receiver that will be decided by this optical fiber. But there are some attenuation dB per kilometer which play important role in order to reduce the transmission distance. Basic attenuation of the optical fiber are absorption, scattering, radiative losses of the optical energy by core cladding loss. So many loss are to be there. So that will basically restrict the transmission distance beyond some limit. So in this lecture, I'm going to explain about the attenuation and the loss which degrade the transmission distance. Uh, there are absorption, scattering, bending loss. Like as information is sent over the long distance, after certain distance, when the information level that is fall below the threshold level, then we require naturally a repeater. But the level of threshold level fall is due to all these attenuation is basically caused by the various kind of the loss of optical fiber, like scattering, bending loss. Scattering is due to both with the fiber material as well as the structural imperfection in the optical fiber. Sometimes there is a loss is also occur when there is a small bounce and variation that are occur in the surface of the fiber. This bounce and variation is called the microbands. So attenuation can be also there when there is a different in the core cladding composition that are occur. So attenuation or loss in the optical fiber, whenever we have to start up from the starting from first window to third window, there is a decrease in the attenuation so that transmission system that can be become a perfect transmission system. The attenuation is continuously goes its lowest limit. Nowadays we use 15 nanometer for the transmission, which is the third window is used for communications. So the attenuation mean to the loss of optical energy, light energy, as light power is travel across the optical fiber from the one end of the transmission to the another end of the reception end. So this attenuation is measured in term of a dB with respect to the length, and dB is used in order to comparison of power level, which is defined as the ratio of input optical power for a particular wavelength to the output optical power, represent in term of a 10 log 10 input power upon the output power. It is inversely proportional to the length of the fiber. So length is just inversely proportional to it. Overall attenuation is defined as the optical input power to the output optical power in a fiber of length L, and it is represented by a 10 log 10 P input upon P output and divided by a L. A logarithmic unit is used at here in order to reduce the calculation for multiplication, division, for all this. Attenuation is caused by the absorption, and here the graph between attenuation and photo energy in electron volt is represent for the various wavelength for intrinsic loss. Absorption loss is represent absorption of the light by fiber depend greatly on the wavelength of the light, used and impurity in the fiber itself. The amount of light absorbed generally decreases with the increase in wavelength. At 850 nanometer, the absorption is around uh, 1.5 dB per kilometer, whereas for 1500 nanometer, this absorption is less than zero point 0.5 dB per kilometer is observed. As absorption is also caused by the atomic defect in the glass composition. The imperfection of the atomic structure of the fiber material, such as missing of molecule, high density cluster of group of cluster is to be formed, although it's have a negligible effect as compared to intrinsic and extrinsic absorption, but there is an effect. Basically, absorptions which we have observed are two category. One is intrinsic absorption, another is extrinsic absorption. Now, in intrinsic absorption, which is the part of this UV absorption as well as the IR absorption. In intrinsic absorption, absolutely pure silicate glass has a little interim of absorption due to basic material structure near the IR region. So it's have a two major intrinsic absorption mechanism at optical wavelength, which leave low intrinsic absorption near this 0.8 to or 1.7 micrometer. So from here to here, fundamental absorption as the peak of which is our center at the UV wavelength region. This is due to the stimulation of electron transition within the glass by high energy excitation. The tail of this peak extended into the window region at a shorter wavelength. So this part of ultraviolet absorption. Another is there is a IR region, IR absorption. This IR absorption is basically due to the presence of OH ion, hydroxyl ion, the chemical bond between atom of the fiber are formed and vibration frequency due to this vibration bond and EM field is transferred of energy from field to this bond. So absorption is quite strong. We have observed from here to here, and due to this is due to the oscillations absorption at silica dioxide 9. It is around in 9.2 uh, micrometer, whereas phosphorus oxide 8.1 micrometer, germanium oxide around 11 micrometer within the glass. Its effect decreases by suitable choice of this core and cladding composition that can be reduced. So another, this is all about the intrinsic absorption. There is another cause of extrinsic absorption. Now, extrinsic absorption is by the impurity atom in the glass material. Practically, optical fiber is uh, prepared by conventional melting technique. So, source of attenuation is the transition metal element impurity. Metal impurity like chromium, copper, they are occur in wash state like chromium 3 plus, copper 2 plus, manganese 2 plus, ferrous 2 plus, nickel 2 plus, carbon 2 plus. This causes attenuation above 1 dB per kilometer near the IR region. So there is a technique, vapor phase architectural oxidation method used for formation of the material by using that technique, these extrinsic loss that can be reduced, these impurity can be reduced. In the case of intrinsic absorption, instead of these oxide glass, there are non-oxide glass are available, that is fluoride, chloride at longer wavelength, which are good for infrared and give a less attenuation as compared to the glass, oxide glass. So if you see from experimental, this is the UV absorption which we have observed by UV and IR absorption, which are observed by this intrinsic absorption, whereas for the extrinsic absorption, there are presence of some of the impurity atom. So this cause there is a attenuation that has to be increases. So this is the baseline of the attenuation, and another attenuation is also added in order to increase this attenuation loss in the single mode fiber that we will discuss. Like absorption spectrum for OH ion due to hydroxyl ion which are present in the silica, and that cause there is a major loss. So because hydroxide ion or these are dissolved in the glass, the absorption peak is occur at 1400, 950 and 725. These are the further their combination of overtones and fundamental silica vibration. These are occur at this 1240 nanometer. Then there is a 1130 nanometer and 880 nanometer. These are the overtones. So at longer wavelength, first overtones that is occur at 1380 nanometer, and its sides at band which is forming at 1240 nanometer. And because this first overtones cause a bigger loss, bigger attenuation in dB per kilometer, absorption gave attenuation of around 2 dB per kilometer part per million and 4 dB per kilometer. Second overtones is around at 950, which gave the attenuation around 1 dB per kilometer part per million of the hydroxyl ion. Longer wavelength region, like third overton is at here, which is observed at around 725. So longer wavelength region around 1300 to 1500 uh, generally which we see 1550 is less unaffected by OH, and here attenuation is only around zero point 0.2 dB per kilometer, and it is approaches to 0.18 dB per kilometer as a practical limit. So further there is a scattering loss. Scattering loss is basically whenever there is a ray that is fall at the core colliding interface, if some of the uh, mm, there is some impurity or some missing molecule or like that is to be formed, the light is strike at here, the energy may be lost in the backward direction, maybe in this direction, maybe in this direction, and this cause there is a light maybe a propagate instead of straight forward, it is go in this direction. So there are a lot of problem that has to be occur, and ultimately the power loss is occur, and transmission phenomena is also disturbed with the scattering loss. There are two type of basically scattering loss. One is linear scattering, another is non-linear scattering. In order to measure the scattering loss is occur due to microscopic variation in the material density, composition fluctuation, structural inhomogeneity, or sometimes there is a manufacturing defect that has to be occur in the fiber. So there are two type of scattering which are further categorized in linear scattering, relay scattering, Mie scattering, waveguide scattering is there. Whereas in the case of this non-linear scattering, there is a stimulated Boolean scattering, stimulated Raman scattering are present. So first of all, we have to start with the linear scattering. Linear scattering basically the mechanism cause of transfer of some or all of the power contained within the one propagation mode to be transferred linearly to the different mode. So this resulted attenuation of the transmitted light as it transfer may be a leaky mode, may be a radiation mode, uh, which basically does not continue to propagate in the fiber core, but it may be radiated out of the fiber. That feasibility is also there. So by this there is a no change in frequency during this scattering. So this cause is occur basically due to the microscopic variation in the material of the fiber. So or any another like there is a composition variation or sometime density fluctuation. All these are the basically cause of this. So first of all, we are dealing with the relay scattering loss. Relay scattering loss is basically the dominant intrinsic loss mechanism in low absorption window between UV and IR absorption till. It results from basically the inhomogeneity of a random nature occur in small scale as compared to the light. So this inhomogeneity is the maybe there is a refractive index fluctuation that may be occur, which maybe arises due to and composition variation which result from the projening of this glass lattice on cooling. And another loss, this composition variation, sometime which is occur, like glass is made of several, it's like a silica dioxide, a combination of that. So, several oxides are there. The composition variation may be reduced if there is a improved fabrication technique is used. Index fluctuation caused by freezing of density in homogeneity that is not included here. Another, there is a microscopic variation in the material that we have unequal distribution of the molecular density or atomic density that leads also to be a relay scattering loss. So if we see that scattering is due to the density fluctuation and produce a attenuation proportional to the 1 upon lambda 4. For this formula is for a single component of glass relay formula in which we use the parameter 8 pi cube 3 lambda 4 n square minus 1 square uh, kb tf bt napper. So this is give the attenuation causes by this relay scattering loss. So alpha scattering value that has to be given. If we have to calculating the relay scattering coefficient, it is also possible. We can calculate it using a relay scattering coefficient gamma r, and that formula is the same 8 pi cube 3 lambda 4. Instead of this n, there is a using n8 P square, this BC, and TF is used, and from that we can calculate the scattering loss. And that scattering loss with respect to the length, that can be calculated, which is equal to a exponential of minus gamma r into L. That formula is how I evaluate it. Further, there is a my scattering. Next is this linear scattering. Under this my scattering loss, this my scattering loss is occur in at the inhomogeneity which is comparable in size to the guide. This is due to perfect structure of the waveguide caused by imperfections such as irregularity at core cladding interface, or there is a core cladding refractive index difference along the length of the fiber. Sometimes there is a diameter fluctuation, strain or bubbles. These are the cause. So in homogeneous, there is a imperfection, fiber geometry or irregularity or bubbles, that has shown there is a fluctuation in the diameter. In this third, there is also shown the fluctuation in the diameter which may be occur, and sometime there is a cause of refractive index difference, that is the part, and sometimes there may be a strain and or bubbles which are to be formed, which cause a scattering, and that scattering is my scattering, as the scattering inhomogeneity size is greater than lambda by 10. So scattering intensity which has a angular dependence can be a very large. Scattering created by such a inhomogeneities mainly in the forward direction. That's only forward direction is called the my scattering. Loss due to this depend upon the material, design, manufacturing. This can be reduced, removing imperfection due to glass manufacturing process, carefully controlling the extrusion of and coating of the fiber, that can be done, increasing the fiber guidance by increasing the refractive index difference between the core and cladding part. So these are the some improvement way in order to improve the. There is a waveguide scattering loss. It is a result basically variation in the core diameter, imperfection of the core cladding interface, and change in refractive index, either core or cladding. So all these cause there is a sometime at the fiber tips the light is just merge out, and the part of the light is to be propagate, and this is basically the light sometime a change in refractive index that has to be occur, look like that glowing part is to be there. So that is also came under the waveguide scattering. There is a transfer of mode basically occur. Further, there is a nonlinear scattering. So nonlinear scattering caused by disproportionate attenuation at a high optical power level. And nonlinear scattering causes optical power from one mode to be transferred to the forward or backward mode in direction to the same or to the other mode at a different frequency. It's depend upon the optical power density and becomes significant above the threshold power level which is to be given. So nonlinear scattering, there is a power transferred in the forward as well as in the backward, that is totally depend upon the frequency. Nonlinear scattering are stimulated Boolean scattering and stimulated Raman scattering observed at high optical power density in the long single mode fiber. So first of all, there is a stimulated brilliance scattering. This is as modulation of light through thermal molecular vibration within the fiber, and scattering appear as upper and lower sideband, which are separated from the applied incident light modulation. The incident photon in the scattering process, there is a produce of phonon, a quantum of elastic wave in a crystal, um, and this phonon of frequency, acoustic frequency, as well as scattered photon is also produced in that process. So this produce a optical frequency shift, which is very scattering angle frequency shift is maximum in the backward direction and reduces to 0 in the forward direction. So SBS is basically the mainly the if we are thinking the backward process, it is significant above the threshold power density. This PB is equal to 4.4 into 10 to the power minus 3 d square lambda square alpha and nu. D is the core diameter, and lambda is the operating, alpha is the absorption, and this nu is the source bandwidth which is used in this having around a gigahertz band. There is another kind of scattering which is called the stimulated Raman scattering. It is similar to the SBS scattering, except here high frequency optical phonon are produced instead of acoustic phonon, in which are generated in the scattering process in case of a stimulated Williams scattering. Here high phonon are produced, high frequency optical phonon. So SR process both in forward as well as in the backward direction. Optical power threshold here having a 3 order of magnitude high as compared to the uh, William threshold power in this particular fiber. This threshold optical power for SRS is equal to 5.9 into 10 to the power minus 2 d scale lambda scale alpha b. Lambda is the operating wavelength, alpha is the absorption, d is the fiber core in diameter, which is represented in micrometer, v is the source bandwidth in gigahertz, which we have used. So next, so bending loss. This loss is occur when fiber undergo a several bend or maybe a long bend around the uh, building or in some metro city. So this loss is exist when naturally there is a lot of bends are to be there in the path. So due to this energy at the bend exceed the velocity in the cladding part, and this will disturb the mechanism of propagation. There are two type of bending laws are there, that is based on the radius of the optical fiber. One is there is a macroscopic bend, another is a microscopic, random microscopic bend of the fiber axis. Now in macroscopic bending, bending in which undergone a big kind of bending at the building. So by bending, there is a increase exponentially as radius loss. This is increases as we have to increase the radius of the curvature, that accordingly these are correlated with each other. And if for this curvature, if there is a, instead of a big room, we have taken a small one. The curvature of radius of curvature that is goes down, and this cause there is a increase in bend up to certain distance, up to certain radius. The bend is made uh, certain more and more, and it is become quite large if we have to reduce that radius. So what happen? The energy basis basically propagate in the optical core of the fiber. The part of the energy is also propagating in the cladding as from the mode field diameter. And what happen at the bend, the outer part, this part will have to move faster velocity, and this part has to move at a slower velocity in order to cope up with the or travel with the optical fiber. So whenever at the bend, it is not feasible that this part of the light or spectrum has to move faster, this has to move slower in comparison to this information. So there is a basically disturbance in the information that has to be occur on the bend, and this will causes a we have not got a right information at the receiving end. So overall, if we consider that this radius r is the radius, and we can say this axis is the information which is away from this center, certain critical distance axis, and accordingly optical energy beyond that axis that will not cope up with this. So it is depend upon only the field which is moving outside this, and also this. So the attenuation is caused by some factor, say C1 exponential of C2 into exponential under the R. As we have to reduce the radius of curvature, that attenuation goes on decreasing. So there is a way how we can stabilize these micro bending laws. One is designing a fiber with a large relative refractive index difference of the core and cladding. That should be a large N1, and it should be a large. By this, that micro bending loss that can be reduced, so that the maximum power that can be propagated only in the core due to this large difference. Another is operating at a shorter wavelength. Critical radius of curvature for single mode fiber can be calculated by this formula 20 lambda n1 minus n2 3 by 2 and 2.4748 minus 0.996 lambda upon lambda c raised to power minus c. Lambda c is the cutoff wavelength for single mode fiber, and all another parameter n1 and 2 these are the core and cladding radius operating wavelength that has to be taken. Now another is there is a microband loss. These microband are the small fluctuation in the radius of the fiber. This cause this cause due to non-uniform manufacturing of this fiber, or sometimes there is a some lateral pressure that may be there, or sometimes there may be some packaging loss due to this information which is propagated when it is at here, and sometime it may be leave, or due to this information may be radiate out from forming a leaky mode in the fiber. There is a bending loss can be minimizing by extruding a compressible jacket over the fiber. When there is a external force is applied, jacket deform only, and fiber will not deform. In this way, bending loss we can reduce. Next is there is a core and cladding loss. Core and cladding loss having a curve. Core and cladding loss have a different index indices of refraction because of difference in the composition. Core and cladding having a different attenuation coefficient alpha 1 and alpha 2, and the loss for a mode of order, say this is the alpha with the order of mode V and M. This power we can represent by a alpha 1 P core upon P. P is the total power, P is the power in core, plus alpha 2 P clad upon the total power. Otherwise, we can also represent P core upon P plus P clad upon P is equal to 1. Uh, P core upon P, we can find 1 minus P clad upon P, or other way. So P core upon P is equal to 1 minus P clad upon P. Whenever we fill this in this expression, then this loss for a mode is equal to alpha 1 plus alpha 2 minus alpha 1 P clad upon P is obtained, and the total loss of the waveguide found by summing all the mode weight by a fraction of power. For graded index fiber, both attenuation coefficient and mode of power be the function of a radial coordinate at a distance r. For that, all another factor are same, but the power in the clad is taken as n square 0 minus n square r divided by, that is the part to total part, n square 0 minus n2 square. So NR is basically the refractive index variation for when R is less than A or R is greater than A. Loss encountered by graded index fiber is equal to 0 to 5 of alpha R into PR RDR and 0 to infinite PR RDR, where PR is the power density of the metal at R. Loss increases with the increase in the mass. So here a loss summary is represented. This is why some cause of loss absorption, then there may be some scattering, homogeneous structure scattering loss may be there that causes scattering, maybe a micro or macro band loss that has to be occur, splices loss may be there before the output end. And here I'm also giving one of the numerical problem. When optical power launch into a 8 kilometer length of optical fiber with power 120 microwatt, the mean optical power at the fiber output end is equal to 3 microwatt. We have to determine overall signal attenuation when no connector and signal attenuation per kilometer. The overall signal attenuation for a 10 kilometer optical link using same fiber with splices at 1 kilometer interval, each giving a attenuation of 1 dB. So first of all, overall signal attenuation when there is a no connector. For that, standard formula is use 10 log 10 the input power and the output power divided by L. L is 8 kilometer. So after 120 micro is 10 raised power minus 6 and 3 into 10 raised power. This is cut and we got a 16 dB from here. Now signal attenuation per kilometer. For that we use alpha is already found from here. We just have to multiply by length. It is already find it. Alpha is there, alpha d, that is 16, and alpha L is equal to 16 dB, alpha L is 8, and we have to find signal attenuation per kilometer, then that is equal to a 16, and we find alpha is equal to a 16 divided by 2, that is 2 dB per kilometer is founded from here. Now total loss is the fiber loss and splices loss. Splices loss are there after every 1 kilometer there is a one splices. So if we see, there are 9 splices to be there. Fiber loss, which we consider here a equal to, the formula is used here is equal to alpha into L. Alpha is 2 dB per kilometer into 10, 20, 20 plus 29 is to be found from here. Next slide we'll discuss in the next lesson lecture, dispersion in optical fiber, which also cause attenuation and also signal is degraded. Thank you.